developer from Navigator to please come up and present and proceed with the meeting.
Thank you for having us. Welcome, everyone. Thank you for your time this evening. We look forward to sharing information about our project and the process and partnerships that we share with ethanol and fertilizer facilities across the Midwest. To start, I want to introduce myself. My name is Danielle Anderson. I live in Bloomington, Illinois, and have spent a majority of my career working for the ethanol producers and the crop farmers in this state. In my current role, I'm focused on meeting with folks like yourselves and ensuring that the project process and values are communicated to you. I am joined today by several of my colleagues from right-of-way, engineering, and our carbon storage. So I will now turn things over to Chris Brown. He's our Vice President of Capital Projects, who will take the next 25 to 30 minutes to discuss the design and operations of our carbon management platform.
What a very nice, large audience here. I'm very glad I did not wear my yellow Navigator shirt today. So, as Daniel indicated, we want to be able to utilize this time to really walk you through the project on exactly some of the finer points that you may not have known about what carbon capture and utilization and sequestration is. And so with the mindset of 30 minutes, this typically takes anywhere from 40 to 45 minutes, so I may go a little bit quick. If you see something during here, please come up to the microphone afterwards and we'd be more than happy to address any of the questions you have in here. What I intend to hit on here is an overview of the Heartland Greenway system. I'll go really quick through that. Most of you are already familiar with that. General properties of the CO2 itself, transportation and safety measures, system specifications, design and operations, and finally the plume modeling overview and release indicators there. So I'd like to start on this slide right here. The Heartland Greenway project is 1,350 miles of liquid CO2 pipelines. And that's all the way from Nebraska, South Dakota, a portion of Minnesota, through Iowa, and down into Illinois, into sequestration here. Excuse me, my throat is dry. Right here, we're sitting right at that intersection right there. That's Sangamon County. The little leg that goes down here, that's the Montgomery lateral, and then this part is our trunk line. We call it the trunk line. It's all the different laterals that feed into the trunk line. It feeds the aorta of the system. That's a 20-inch diameter pipeline. Starts 16 and is 20-inch, and that's what takes all the sequestration from all the little yellow dots there. The yellow dots are the different capture points. Those are ethanol plants, and we have one fertilizer plant. And what we're doing is we're capturing the actual plume, the CO2 plume, off of their stacks on the ethanol plants. And these are some of the customers that we have in here. So what is carbon capture? So there's 4 different things here. This is an ethanol plant right here. This structure right here is what we intend to build at each of those 21 locations. And what it amounts to is you drive down the road, you see the plumes coming off the top of the stacks. We will physically catch that and run it through about a 30-inch diameter ducting or stainless steel pipe to a series of blowers. These blowers will take that from atmospheric pressure to increase it up to about 15 psi, and it will enter into a 4-stage reciprocal compression skid. That reciprocal compression skid will bring that pressure up to eventually 1,400 psi, but as it goes through each of the stages, from 15 to, let's say, 250, from 250 to 500 to 700 to 900. After each stage, the CO2 is hotter. It gets hot through the compression, so it'll run through what we call heat exchangers, or basically coolers. In that cooling process, it's dropping out water. It's very important to remove the water from the CO2 stream. After the 3rd phase of the compression, it'll actually go through what we call a DEG dehydration skid. And that will take the majority of the water out of the CO2 train, because you do not want to have water, which I'll get to in a minute, in the CO2 stream. So after it goes through the 4th stage of compression, it exits at approximately 1,400 psi. It'll then go into what we call a horizontal pump. That pump will take that 1,400 up to the intended operating pressure of 2,100 psi. Now the maximum operating pressure is 2,200 psi, but we intend to operate at the 2,100 max psi. Before it goes into the 2nd stage, which is the midstream infrastructure, that's the pipeline, it'll go through what we call the custody transfer assemblies. One of those is a meter. It'll meter exactly how much flow is going past that point, but most importantly, it has to pass a series of analyzers that we have in place. And it'll be gas chromatographs. We will have an O2 analyzer, an H2S analyzer. We will have H2O or water analyzer. And all of those things are ensuring that the actual quality of that CO2 meets our quality specification. And if it doesn't meet our tariff or quality specification, The system will be shut in, the CO2 will go back to the plant and go into recycle until we can figure out what's going on and adjust the system so it can enter the actual midstream. Excuse me, my voice. So now we're in the pipeline. I'm going to speed up a little bit. We're in the pipeline here. There's opportunities for utilization. In the future, if we have like a truck offtake, it could go to dry ice. If the sustainable aviation fuel, it's a big thing in the industry right now. You could have a direct connect to them to provide CO2 for them for their utilization. Or ultimately, right now, the vast majority is going into sequestration. And we have experts in sequestration here tonight, so if you have any questions, you can refer to that. But I'm going to stick to the midstream part because that's what I'm responsible for as far as my particular job there. This is very important, but I'll go quickly through it here. This point right here is called a critical point. And that critical point is at 87.8 degrees Fahrenheit and at a pressure of 1070. So our minimum operating pressure we intend to have on the system is 1300 psi. And the reason we have that set is we want to remain in this supercritical and liquid state here. If you get below those down in here into the triple point, that's when you could have anywhere from the gaseous state. So we're always going to be focused on being in that supercritical fluid because that's how you transport CO2 efficiently. Just a little bit of history. I think everybody's heard there's 5,500 miles of pipelines currently in place for CO2. This is just a couple of examples that are up here in the Midwest areas. But more importantly, these are considerations when designing and developing CO2 transportation. I mentioned this right here, and I'll come back to here. The removal of water is key. You do not want to have water in it. That's why we will have the water analyzers. We will not let anything get into the pipeline with the CO2 stream that even has a chance of having any water in it, because you do not want to combine the water with the CO2. The susceptible to ductile fractures. Per code, we are regulated by PHMSA, which is the Pipeline Hazardous Materials and Safety Administration, Part 195 specifically there. Part of that requirement is that you need to ensure that the pipeline itself is conducive to being able to, is conducive to be able to transport CO2. And so to do that, you have to perform what we call a metallurgical analysis. So we actually look at the chemistries of the pipe. We ensure that it is both passing from the ductile standpoint, but also to be susceptible to fracture propagation. Fracture propagation means a zipper. If something were to happen and to the pipeline that was punctured, if you do not do the correct chemistries or design it to be able to withstand fracture propagation, that's what people call the zipper effect. So we have gone through this exercise at the very onset, developed our pipeline spec, and our result of that is we have a very, what we would call an over-designed pipeline in regards to what PHMSA requires from a Part 195 standpoint. We end up with heavier wall thickness pipe, we end up with heavier yield, we have what we call larger Sharpie V-notch requirements when you roll this at a pipe mill. All of these things will be regulated as when we're making the pipe. You have inspection spots, and we ensure that that pipe that we actually have designed is in accordance with preventing any type of fracture propagation. The other thing here is just in the event of a loss of containment, if you're at that pressure in the liquid state or the dense fluid, it will turn to vapor. It'll go from the 2100 psi to atmosphere. You'll see what you've seen before. It'll turn to water moisture, and then the CO2 will actually turn into the gaseous form. So if you go back up to that chart, you would end up being back down in this zone right here if something were to be released. So if you do an intentional blowdown, you'd see it in the form of a gas. So, from ethanol plants themselves, coming off their flumes, are already 98% pure CO2. That is why this is such a good thing for the ethanol industry, is that they're able to lower their carbon scores by taking advantage of sequestering their actual fermentation off of their ferment, or their food off their fermenters. The line pipe, as I mentioned, is designed especially for CO2. We went through the very laborious process of designing that so that it is compatible with CO2, and it exceeds the requirements of API 5L PSL2. And that's fancy terminology, fancy code for line pipe design. The federal regulations, I mentioned this already, by 195. We're also including DNV, that's Det Norske Veritas. They're a company that's very well known for being knowledgeable in regards to CO2. They do experiments on it. They provide safety guidelines. We're also utilizing their recommended practice F104 as a basis of part of our design, in addition to portions of Part 192, which is a part of PHMSA there. Normal operating pressure 1300 to 2100 psi. Again, the maximum operating is 2,200 PSI, but we're holding that 100 off the top end there. The pipe depth is 5 feet. By PHMSA, typical pipeline depth for PHMSA is 3 foot in the ground. We're exceeding that by 2 feet minimum in areas, and a lot of areas will be deeper, which I'll get to here in a minute. The diameters themselves, they range from 6 inch to 20 inch. Our trunk line is 20 inch as well as 16 inch. The little laterals that I showed you on that other drawing, they range from anywhere from 6 inch up to 12 inch on the laterals themselves. Have an operating temperature of 40 to 110 degrees Fahrenheit, and the mainline valves. So this is very important. Last year, PHMSA came out with a modification to their rules. And they came out, and this is for Part 195, not just for CO2 pipelines, this is for all of Part 195, which is all hazardous liquids. They came out and they said if your pipeline goes through an area that contains a high consequence area, your maximum distance between isolation valves is 7.5 miles. If your pipeline goes through an area that does not contain a high consequence area, then your maximum distance between the isolation valves is 20 miles. So this just came out last year as far as being actual code. All hazardous liquid pipeline operators have to adhere to language that PHMSA implements as far as changes to our code there. Ultimately, our goal in routing this thing was to route to minimize the collective impacts to HCAs. And again, an HCA is a high consequence area, vulnerable places of gathering or other stakeholder inputs there. To give you a little bit of example of what an HCA is, it's commercial navigable waterway, let's say Mississippi River, Illinois River, high populous areas, right here in this town, Springfield, other populous areas, groups of clustered suburban areas, and unusually sensitive areas, and or drinking water areas. So we overlay the analysis of our HCA components onto our pipeline alignment, and we're able to see where an HCA would intersect into the actual pipeline center line. And that allows us to say, okay, in this section right here, we have an HCA. Our maximum valve distance can be 7.5 miles at the max. Typically, what I've seen from the standpoint that I'm involved in both the engineering and the PM, is that on average in areas where we have HCA, our average valve spacing is 6 miles, between 6 and 6.3 miles. In areas that we do not have HCA, we're nowhere near the 20 miles. We normally range from anywhere from 13 to 15 miles in an area that's wide out in the open there. A couple things to focus on right here. This installing EFRDs. When we laid out our valves, which we have met with the emergency management teams for each of the counties, we've kind of showed them our initial HCA valve placement. That's not the only valves we'll have on the system. We'll also be installing what we call emergency flow reduction devices, and that's what an EFRD is. And that could be a check valve. You've seen check valves in plumbing. It's got an arm lever up. If it loses pressure, this comes down, and it prevents any backflow from happening on it. So in essence, a check valve is a dumb valve. If something were to happen and you lose pressure on the system, that flapper would go down and it would prevent any of the product from coming back on the side that has no pressure on it. An EFRD could also be a ball valve, which we control via our control room as well. A couple other things on this slide, and then I'll move into some more of the details here, is the better monitoring of cathodic protection. After this pipeline is installed, it's in the ground, it's in the operating mode. It's just not left there. With steel, you have to protect it. And this is not just for CO2 pipelines. This is for all pipelines. You have to have a cathodic protection system put on the pipeline. The pipe itself will come out with state-of-the-art fusion bond epoxy coating. The pipelines that we install via horizontal directional drill and or boring, which I'll get to in a minute, they will actually have that 14 mils of fusion bond of epoxy, and they'll also have about 30 to 40 mils of an abrasive-resistant overlay, and that just protects it for when you're installing it. The cathodic protection, if something were to happen after you install this pipe, and let's just say when you lowered it in, it hit a stone or something, you have a very minor little tiny hole in that coating. That current is actually a current that's attached to anodes, and the anodes will actually be attached to the pipe. So if something were to happen to that coating, that anode, or that current, dreams that anode, and it patches and repairs and blocks that pipe from actually oxidizing or rusting. So that's important, and that's required by PHMSA, and that's one of the things that would be on the pipeline to ensure that it does not have corrosion from the external standpoint. From the internal standpoint, after we get this entire system built for each of the legs, we will run a tool. It's called a SWAT pig. and it's an actual tool that you run inside the pipeline. And if you can imagine that it's measuring 360 degrees all the way around, the wall thickness all the way around the pipe, every inch of the pipeline. And after you've done all your inspection, when you're designing it, when you're welding it, when you have it on the bank, when you're lowering it in, you're hydrostatically testing, which I'll get to, after you do all this stuff and you run this smart pig, you're not anticipating to find anything. But what it serves as a baseline. Because by PHMSA, you're required to come back on a 5-year basis and run a pig again to check and see if you have like any internal corrosion. Navigator is committed to shortening that time frame. We intend to run it every 3 years. So when we come back on year 3 and we run those smart pigs again, we take that data from that smart pig and we directly overlay it on day 0. And we can see if there's been any type of corrosion from the internal standpoint. So you have the smart pigs handling the internal, you have the cathodic protection protecting the external. So I just want everybody to understand that it's not just lay that pipe and walk away. There's a continuous protection of that pipeline throughout the life of the pipeline itself there. Let me get through here in case I run out of time. So again, I mentioned avoid to minimize the high consequence areas. We ran multiple plume dispersion models, and we utilized 2 firms to do that, Integrity Solutions. They utilize the Aloha method, which is the aerial locations of hazardous atmosphere. A lot of the EMS teams from the counties we've met with, they're very familiar with Aloha. We also use DNV's proprietary FAST program. That's a PHAST. And we ran these scenarios, well, let me save that because that's going to be talked about in another slide. Right here on the depth of cover, we talked about that. We follow the existing utilities when we can. A lot of people ask us, well, why didn't you follow this pipeline that's right here? And I said, well, our primary objective was to maintain, the maximum offset as possible from any type of an inhabitable structure. And so even if there's a parallel line that's going through a power line or a pipeline, we would parallel those when we could because people are familiar with those areas and it prevents the likelihood of people trying to encroach upon it. But if it was up against a residence or a house, we would come out away from that to try to maintain the maximum buffer distance that we could design there. I mentioned that increased factor of safety. This kind of gets a little bit, from an engineering standpoint, PHMSA requires, or you have to have your design at a 0.72 maximum, sorry, minimum, maximum. So basically the pipe can only operate at 72% of its actual potential strength. Like if you just had a piece of pipe, that thing would be good for 100%. You can only operate at 72% of what that value is. When we did this metallurgical analysis and did everything with that, we have found that we are significantly under that 72%. So we're only operating at 63% for the 20-inch diameter pipeline of what it's capable of operating at. So it's capable of operating well into the 3,000s, but it's operating at 2,100. And on the 6-inch, we're only operating at 49% of what it's capable of operating at. So that's good for over 4,000 pounds on a 6-inch. So that's just an example of when we went through that metallurgical analysis, it actually resulted in higher yields and actually higher wall thickness of the pipe, which allows for a safety factor embedded into the pipeline system there. The 24/7 monitoring of CO2 composition, I mentioned that. Those monitors, or those analyzers at each of those capture locations, they are fed into our brain, our local brain there. It's called SCADA, Supervisory Control and Data Acquisition. That is continuously monitored. If something were to happen, if there's an upset in the plant and that alarm goes off, that valve closes, and that gas or that CO2 is not allowed to enter the system there. This is an important thing to talk about. You do have so many steps along the way when you're when you're building this pipeline out in the field. We have dedicated inspectors for trenching. We have dedicated inspectors for backfill, installation, welding. We even have dedicated inspectors for drain tile repair. We'll have specialists out there, coming behind the main contractor, putting in a temporary repair to allow to put the pipeline in, and then a permanent repair after the pipeline is in place, and to ensure that the drain tiles are returned to their as good or better condition. The hydrostatic testing is what you do at the very end. So you've got everything in the ground, you've done all these checks and balances, and all these are recorded on documents that are reviewable by PHMSA when they come out and do an audit. Now you're ready to say, okay, the pipeline is in the ground. We're going to test it. So we fill the pipeline with water, and we bring that pressure up to 1.25 times of what is the maximum operating pressure. So we'll bring that water up to a pressure of 2750, and we'll hold that water and that pressure in that pipeline for 8 continuous hours. And during that, we'll have charts that are recording that pressure, we'll have charts that are recording the ground temperature, the air temperature, and we'll have a log of every reading that we make on that pipeline. That record, that hydrostatic test record, will become the actual asset record for the lifetime of that project. Now, if something were to happen in the future when we run one of these pigs, and we go out there and replace, let's just say we replace 10 feet of that pipeline, that 10 feet has to have its own hydrostatic test, and that comes in conjunction with the previous test as far as the hydrostatic test records. When PHMSA audits us, which they audit every pipeline company, that's one of the first things they ask to look at is where are your hydrostatic test records? Because that tells the test, you're ensuring that that pipeline is capable not only of handling the actual operating pressure, but 1.25 times the operating pressure there. How am I doing on time?
You have almost 11 minutes.
11 minutes, good, thank you, sir. So, give you a little bit on the leak detection. Leak detection is very important in regards to not just CO2 pipelines, but any pipeline system. We will have what we call a continuous and a non-continuous. The non-continuous is real simple, I can explain it. We'll have aerial patrol about roughly every 2 weeks. We'll have an airplane or helicopter or drone. We'll fly the route, and what that will tell you is if you had like a series of bad weather events, the pilot or whatever mechanism you're using, it can detect whether or not you have some erosion on the pipeline system. Boom, get out there, you send an operations team out to inspect it to make sure the pipeline's safe. The other thing is like any other utility is through Illinois here, it'll be involved in the 811 plan. If someone's planning on doing something, they'll call 811, ticket comes into Navigator, they have to go out there and make sure that whatever's going to be taking place is not going to impact the pipeline. But during the course of that, they're also patrolling the right-of-way. They're continuously patrolling the right-of-way day in and day out. That's the non-continuous. The continuous is a combination of a series of technologies that we are going to blend together. The compensated mass balance and the RTTM, which is real-time transient model. This right here, we're modeling the entire system, all 1,350 miles of it, every mainline valve, every booster station, every capture location. So there'll be an actual model. And the compensated mass balance is a very scientific way of saying what comes in must equal what comes out. So everything is measured into the system. It's measured through a series of algorithms and pressure equations, and we see what's coming out. And that's how you can determine, okay, do we have any losses on the system? We also have what we call negative pressure weight. We'll install those in sensitive areas. There'll be sensors, actually transmitters on the mainline valve settings, which if they detect any type of pressure reduction or any type of thing, it's detecting the wave on both directions. And it pinpoints the location of where there could be a potential leak there. CO2 monitoring at above ground facilities, the boosters, the captures, even the mainline valve settings will actually have an actual monitor that'll be there that if it detects CO2, it's going to trip a signal and it's going to send it to the SCADA. And then finally, the fiber optics. In certain areas where we're able to install this, in primary areas and areas of high consequence areas, we will install an actual cable in the same trench as that pipeline. And what that cable will do is very high tech. It picks up fluctuations of temperature, vibration, acoustic, and pressure. So it'll even detect if someone's encroaching upon, like if someone's driving over the top of the pipe with some construction equipment, it'll detect temperature changes. If you were to have a leak on your pipeline system, the CO2 from that liquid state going out to the atmosphere, it'd change the temperature very quickly and very cold. All those inputs feed into that same thing I mentioned earlier, the brain, the SCADA, the supervisory control and data acquisition. There'll be a SCADA box at all these locations, the mainline valves, the boosters, the capture location. That feeds and networks into our control room system. So we have a control room that's monitored 24 hours a day, 7 days a week, 365 days a year by qualified personnel. They get a signal that comes in, they're able to say, hey, we may have an event happening right here. At that point, they will follow their emergency manual procedures along with the counties if it involves getting them involved. And they're able to push a button for all these valves that I mentioned earlier, the HCA valves. Those are all remote controlled valves. So we'll have redundant power and redundant communication to those valves. So if we were to determine that we had an incident on the pipeline, such as a rupture or even a leak, we are able to push two buttons or a series of buttons, and we're able to close a valve on the upstream side and the downstream side, thus isolating that pipeline section I want to get to the plume stuff. Okay, I mentioned that. So, the plume model. The plume model is very important when it comes to CO2 pipeline. This right here, this is part 192 with the natural gas pipeline. It's very clear and concise information from PHMSA as far as that's begun. It's called a PIR, or potential impact radius. From the plume model assessments, as I indicated previously, we utilized 2 independent companies with unfavorable conditions, and we took the worst result of the worst one. So what that means is we didn't cherry pick it. Whichever one came out with the worst result from the plume study analysis is what we use for our various buffers. And when I say buffer, these actually correspond to distances here. Like the first one being the initial routing. That initial routing distance for each of the diameters is what we targeted on trying to have from that distance to any type of structure that's inhabitable or any type of area, a house, church, or something of that nature. The next one is design and operation and mitigation. We also tried this, it's an increased distance. Anything between this point and down, if we weren't able to maintain that buffer distance, is when we would utilize enhanced engineering. Enhanced engineering could be anywhere from thicker wall thickness pipeline to HDD, the installation via HDD, or even additional valves or more operational inspections timelines. The next one, emergency response. From this line all the way down is where we would be engaging and working directly with each of the county's emergency response teams. We've already come out and met with them a couple times and introduced ourselves. We had a CO2 training in the beginning of this year. In the fall of this year, they're coming back to actually start working directly one-on-one with each of the counties on their emergency response plans. Each county's emergency response plan will be designed specifically for that county. You can't do everyone's the same because they're going to have different valve settings, different locations, different hospitals, etc. And then finally, the potential the public education. Everywhere from that one down, or at that point, is when there would be a notification, let me jump to it, on what we're trying to develop right here is a NAV 911 system. We're trying to work out the logistics on that, so if something were to happen from that distance in, it'd be like an Amber Alert, a robocall. They'll be able to go out to the residents in that particular area that they're notified that there's something that could potentially be happening on a pipeline there. Done. 4. Okay. So I want to go back to something real quick. The horizontal directional drill case, that's a technique that we utilize to install a pipeline to avoid any surface impacts. The 98 to 99% of all the main streams and our water bodies that we're crossing, we would be crossing via the horizontal directional drill. You actually drill in on this side and you pop out over here and you use some tools and you widen this hole. You have it on the pipe and you pull it in there and there's no impacts right in here. So I use my hands a lot, so excuse me for that. So that's a horizontal directional drill which you can utilize quite frequently for avoiding anything of that nature. Railroads, very large interstates. The bores, or the road crossings themselves, county road crossings, we adhere to every part of the county. Whatever their stipulation requirements are, every asphalt road we will actually utilize what we call a road bore. We'd excavate a bore pit on either side of the road itself. We'd lower in a machine. It'd bore beneath the road. That's on average a minimum of 10 foot deep beneath the road. That 5 foot is measured from the parallel ditch. And we also get below the utilities. We maintain it anywhere from 18 to 24 inch. If there's a water line, if there's a cable, a fiber optic, we're trying to maintain that distance as well. That translates into a pretty deep ditch in there. So permitting wise, we adhere strictly to the county. If a county has a gravel road and they want it to be bored, it's going to be bored because we are going to permit every one of the road crossings through the counties themselves in there. So.
Still have about 2.5 minutes.
2.5 minutes? Okay. What can I go back to? Dang, that makes you nervous on your clock up here. I know I kind of went through there rather quickly, but again, a lot of thought has gone into this thing as far as the plumes study. I know a lot of people here may be talking about the plumes tonight. Really, that is the basis on which we designed this pipeline. It was to minimize the collective impact to anything out there in the area. And by doing that, we utilized our plume analysis from our independent studies with the 2 different companies there. And that really lines out being able to have the offset distance. When we could not do that, and I'm not going to stand up here and tell you we were able to do that. I know for a fact, in fact, in Sangamon County, I know for a fact, we weren't able to maintain that distance in Sangamon County in quite a number of places. That's where we would increase the engineering or increase the safety design of the pipeline system itself.